Hi everyone, I'm Dinglan. Today I'm presenting our work Pegasus, which is a framework for transparent communication optimization. Modern cloud software is increasingly built on loosely coupled applications that communicate with each other for better modularity and scalability, as seen in popular design patterns such as microservices and serverless computing. For example, one application may be connected to a Redis in-memory database via its network interface. Another example is a reverse proxy such as Nginx, and the application it serves for functions such as TLS encryption or authentication. We summarize this pattern of software as symbiotic processes, which are multiple processes that function coordinatedly and communicate a lot with each other. Symbiotic processes, as shown in these examples, are ubiquitous in data centers. The pattern of loosely coupled symbiotic processes brings many benefits. However, these benefits also come at a cost, due to higher communication overhead for both local communication that happens within a node and remote communication that is across nodes. According to Google's profiling, more than 27% of CPU cycles in data centers are spent in user space overhead related to communication, including data copy or serialization. And another 20% of cycles are spent in the kernel, many of which are for I/O. The data shows that communication overhead is significant in data centers. As a result, optimizing communication is critical to improving the efficiency of the cloud. Ideally, communication optimization for symbiotic processes should meet the following goals. Firstly, we should achieve transparent optimization without application modification. That is, we need to provide a compatible API that most developers use, such as the POSIX socket API. Secondly, we should keep security and reliability guarantees for applications when we optimize communication for them. Finally, we should keep compatibility with existing cloud infrastructures. For example, we would want to integrate a communication optimization system with Docker or Kubernetes so that we can get performance improvement without changing our way of deployment. Pegasus achieves all these goals by optimizing applications such as Redis or Nginx with kernel-bypass networking transparently and securely by up to 442% in throughput with a totally transparent Docker interface. Before showing how Pegasus achieves this, let's first have a discussion on existing works for communication optimization regarding these goals. Many of these works identified OS kernels as an important source of communication overhead. The first approach is to accelerate remote communication with kernel bypass techniques such as DBDK. This approach allows applications to directly access the network interface cards with user space POL mode drivers to get rid of the kernel from the remote communication data path. This can significantly reduce latency and improve throughput of remote communication. The second approach is to co-locate applications on the same node so that faster IPC mechanisms such as shared memory and futex can be used for local communication. Also, the performance can be further improved by running multiple applications in the same runtime process to bypass the kernel overhead for communication, especially for some managed languages. For example, the serverless platform Cloudflare Workers use one single runtime process to run multiple instances of the V8 JavaScript engines, each of which serves one service function to reduce the overhead of communication. These two approaches provide acceleration to communicating programs by bypassing the kernel for communication. However, they have several problems that prevent their deployments in real-world scenarios. Firstly, they usually depend on their specialized APIs or rely on some specific languages or runtimes, so that developers cannot easily port their applications without high rewriting efforts for these systems. For example, in our evaluation experiment, porting Redis to kernel-bypass networking platforms such as Dynamic kernel or FStack requires modifying thousands of lines of code. Moreover, these specialized APIs are not even the same for two kinds of communication. This hinders the flexibility and configurability for developers to deploy their applications with different orchestrations, because they must decide which interface to use before development and deployment. Finally, while eliminating the kernel from the data path, these approaches also lack isolation provided by the kernel. Thus, a vulnerable application can propagate its bugs to other applications. Also, as kernel-bypass networking systems typically depend on direct hardware access via user space drivers, which is without isolation, a buggy application can cause an attacker to gain the access to the hardware. This causes degraded reliability and the security guarantees compared to the traditional architecture of using the kernel for communication. For example, a recent work, Junction, has also proposed using a compatible API for applications, but it uses a threat model of fate sharing, which is less ideal with regards to our security goal. These challenges inspire us to explore a unified and practical way to apply communication optimization securely. Our approach is to apply both local and remote kernel bypass FastPass on multiple communication-intensive Linux programs. We co-locate and fuse symbiotic processes to apply local FastPass by eliminating the kernel IPC overhead, and then apply remote communication optimizations for the communication across nodes. By doing so, we prevent the kernel, which is highly complex and not specifically designed for communication-intensive applications, from slowing down the data path of these applications. Thus, communication can be completely handled in user space without costly switches and invocations to the kernel. Also, for both kinds of communication, we use the POSIX socket API so that the acceleration is transparent for programs, as most of the applications nowadays use the socket API as a unified interface for both local and remote communication. Thus, developers and the users don't need to change their applications to apply communication optimizations. Finally, we apply isolation techniques to prevent the propagation of faults and vulnerabilities between applications. We have a few challenges to address to achieve our approach. The first one is, how can we virtualize multiple Linux programs in the same address space in user space? To address this challenge, our approach is to implement core OS functions in user space, instead of depending on OS kernels for such functions. We implement a user space monitor for performance-critical functions related to process communication, such as scheduling and networking, and other common functions used by Linux programs, such as memory management and signal handling. These FastPass data paths are shown in red arrows. For other functions that are not important to communication performance, we still fall back to the Linux kernel for handling them, as shown by the green arrow. The second challenge is, how can we make the optimizations transparent to programs so that users don't need to modify their programs to use our system? Our approach is to implement the Linux API as the interface between programs and the monitor. We use system call interception techniques such as second filters and dynamic system call rewriting to intercept programs' system call invocations and execute them in the monitor. Then we implement our user space monitor following the Linux API, including the ones for system calls and signals, and also the one for program loading, to allow unmodified Linux binaries to interact with the monitor as if they run on the Linux kernel. The last challenge is that since we put multiple programs in the same address space, how can we prevent propagation of bugs and vulnerabilities between programs so that they don't affect each other? Our approach is to apply efficient in-process isolation techniques, namely Intel MPK for memory protection and the microswitch, which is our prior work for kernel resource isolation. The monitor and each program has their own isolated domain for memory and kernel resources. We enforce in-process isolation to achieve in-process privilege levels. The monitor is privileged and can access programs' resources, while programs are unprivileged and cannot access resources outside their own domains. Also, we handle signals generated by hardware exceptions, such as segmentation faults, to avoid one crashing programs affecting others. Based on these approaches, we propose Pegasus, a system for transparent kernel-bypass networking for both local and remote communication. Pegasus is designed to achieve real-world deployments with zero porting efforts, and can run multiple unmodified Linux programs in the same address space with both local and remote fastpass. Also, Pegasus supports the OCI Container Runtime API, and can be integrated with real-world container runtimes and orchestration platforms, such as Docker and Kubernetes. In our evaluation, we have deployed Pegasus on many common real-world applications used in the cloud, such as Redis, Memcached, and Nginx. Pegasus uses the Linux API to avoid any application modification. It applies in-process isolation to ensure security and reliability guarantees. And it can be integrated with common cloud infrastructures and support a container interface. More design and implementation details are discussed in our paper. Now let's have a brief demonstration of Pegasus to show that Pegasus can accelerate local communication by fusing applications. We first run a TCP server and a client using Docker to measure the ping-pong latency. So the latency is, you can see, 33 microseconds. Then we use Pegasus to run and fuse them. And the latency is only about 1.2 microseconds, which is much lower than the baseline. This demo shows that Pegasus can accelerate communication performance by simply specifying a different runtime, without any change to the code or deployment. Pegasus can transparently support many real-world applications, including ones using a large and complex interfaces. For example, we can even run two GUI programs, Xcalculator and Xclock, in the same address space with Pegasus. This cool example shows the compatibility of Pegasus even for programs outside its intended scope of applications. Now let's move on to the evaluation of Pegasus. The first evaluation experiment is for the latency of synchronization primitives and local and protocol operations between two semiotic processes with local communication. In this experiment, we measured latency for different operations, including a condition variable wake-up or Redis set operation, under both Linux baseline and Pegasus, to evaluate the local communication optimization by Pegasus compared to Linux IPC mechanisms. From the table, we can see that Pegasus reduces the latency by 20% to 85%, which means much lower overhead for local communication. Another experiment is to show that Pegasus accelerates both local and remote communication. We use a combination of a web server and a TLS reverse proxy for the experiment, as an example of a common pair of semiotic processes. We measure the average latency under different throughput with both the Linux baseline and 3 configurations of Pegasus. The first configuration is Pegasus with both local and remote fastpass enabled. The other two are Pegasus with only one enabled. From the figure, we can see that both optimizations are important in the performance gain of semiotic processes that have both kinds of communication. In total, Pegasus achieves 222% improvement in throughput for these applications. In conclusion, we propose Pegasus, a framework for local and remote communication optimization. Pegasus transparently and securely accelerates communication-intensive applications without changes to their code and deployment, and achieves up to 222% throughput improvement for real-world applications with a zero deployment effort. Please check Pegasus artifact using the link, which contains examples of deploying real-world communication-intensive applications as shown. Thank you for listening, and now I'm open to the question.